So now let's talk about heat transfer resistance. You've seen Fourier's rate equation before, and I presented it to you as negative Ka delta T over delta X, and now I'm going calculus on you, right? I'm changing it from a delta to a D, a differential temperature change. Well, what's going on here? Well, it'll all make sense in a minute, but this is the way that the equation was originally stated in terms of it being a differential equation, that the rate of heat transfer conducted through a body is equal to negative Ka delta T over delta X. In other words, the thermal gradient in the direction of heat transfer. Now, on the left, you'll see a picture of a slab. Now, this slab is not a sandwich. It's not three separate materials. It's a solid slab of material, and heat's being conducted from left to right. And you'll notice that the driving force for that heat transfer is the difference in temperature, T1 to T2, across this, let's just call it a wall or a slab. And so this dt by dx, this is really the differential drop in temperature for a differential move forward in position along the direction of heat transfer. And that's really the way the equation was stated. Now, differential equations themselves don't necessarily help you a lot. The integrated forms are what are usually typically quite valuable. So if we integrate this equation across the entire wall thickness, then we end up with what I showed you before. Q dot equals Ka delta T over L rather than a delta X. Remember, the negative sign was just because temperature drops in the direction of heat flow, and so we needed that negative sign. So we've got T1, which is higher than T2, so the negative sign is taken care of there. So, okay, great. So we've seen Fourier's rate equation again, but we could state it a little bit differently. We could rearrange the terms and write it in terms of a resistance to heat transfer instead of saying conductance all the time, instead of talking about thermal conductivity K. As a matter of fact, there are some other terms that we would group together to call resistance. Now, why would we do that? Well, it has to do with the fact that we like to think of this with an electrical analogy. Most of you have studied electronics by this point, I hope, and if you think about a resistor with current flowing through it, hopefully you realize that the reason current flows through it is because of the electric potential difference across the leads of the resistor. And so to begin to help you understand this, you can think of it in terms of fluid flow, you can think of it in terms of electrical flow, but it's the potential difference, the thing that's causing something to happen or causing flow to happen, is the electric potential difference across the resistor. And that potential resistance, or that potential difference across the resistor, causes a flow of charge. And we call that current. That's I. Did you know that I, the current flow rate, is a rate? Just like Q dot is a rate of thermal energy transfer. Okay, so the analogy hopefully is beginning to make some sense. I, the current flow rate, is analogous to Q dot, the heat flow rate. And the voltage difference across, or the electric potential difference across the resistor, is analogous to the temperature difference across our wall or our plate or slab. So the temperature difference is what I would say is the driving force for heat transfer, just like the electric potential difference is the driving force for charge flow. So the last element to make sense of is the resistance. In Ohm's law, it's just I equals delta V over R. You may know it as V equals IR, but it's really delta V equals IR. It's the difference in electric potential. In the heat transfer world, we've got Q dot. That makes some sense. That's the resulting flow. We've got the driving force for heat transfer, the delta T, the difference in temperature. But the conductive resistance, well, that's L over Ka. Well, what does this mean? Well, think about it this way. Hopefully your intuition understands that if that slab gets thicker and thicker and thicker, well, then the gradient's going to decrease. In other words, the temperature drop is still the same magnitude, but now it's farther apart. So it's like a hill that's not as steep as it was before, you see. And so the corresponding rate of heat transfer goes down. So it makes sense that L would be in the numerator for resistance, because the greater the thickness, the greater L, the greater the resistance to conduction. On the other hand, the more thermally conductive the material is, the lower the resistance, and so it makes sense that it would be in the denominator. So K is in the denominator. What about the area? Well, the more surface area available for heat transfer, you know, given the same temperature, T2 across all of one face and T1 all across the other face, the higher the rate of heat transfer, because there's just more area for the heat transfer to take place. So hopefully this resistance to conduction makes some sense to you intuitively. We can also write heat transfer resistance for convection. So in a convection type of situation, we've always got some solid in contact with a fluid. Now remember, when I say fluid, I can mean a liquid or a gas. And so there's heat flow. Let's just talk about heat flow from the surface of the solid, saying that it's warmer, out to the bulk air. Well, the driving force for heat transfer is the difference between the surface temperature and the temperature of the bulk air far away from the surface, where it's essentially unaffected by the surface. So we still have this Q dot flow and delta T driving force that is analogous to the current flow I and the voltage difference respectively, but now the convective resistance has to be written as 1 over HA. And of course, remember, we're rearranging things so that it looks kind of like Ohm's law. So it's I equals delta V over R. And we're just figuring out how to compute the resistance of our thermal resistors now. That's all we're really doing. So the convective heat transfer coefficient, the larger it is, obviously the larger the heat transfer rate, the lower the resistance. Makes sense that it's in the denominator. And the area of the solid is the same as it was for our conductive heat transfer problem before. It's the same argument, right? That the more area you have, the higher the heat transfer rate will be. So it makes sense that both of those terms will be in the denominator when we're trying to calculate a resistance to convective heat transfer. Now there is also in your book discussion about a radiative resistance. I don't like it because the value of that resistance is a function of temperature. Technically, you could say so is the heat transfer rate in convection, because the convective heat transfer coefficient often includes temperature in some way. But it's more of a direct dependence in the radiation resistance and is more important. So I don't really like that, but the one thing you need for your intuition is to realize that most surfaces not only will conduct heat away by convection, and I said that badly, I should have said most solids will convect heat away, they also radiate heat away, say if they're at a higher temperature. On the other hand, if they're lower temperature, then it's in the other direction. There's convection and radiation going to the wall. But you can look at the 2 pages I've referenced there in your text for radiation resistance. Again, I won't use it much, I just include it in the slides for completeness.